Thank you, Roberto, for this wonderful initiative. Sorry again for the mistake with the timing. I hope I can recover. And so I am Gianvito Scaringi. I am from Italy, but I work at Charles University, Universita Karlova in the Czech Republic at the Faculty of Science, at the Institute of Hydrogeology, Engineering, Geology, and Applied Geophysics. My research concerns, of course, landslides, but not only. And the topic I am presenting today actually comes a little bit from farther away, because it is something that I've begun to study since my time at the university, since my master's degree and then my PhD, and it concerns the effects of chemistry, the chemistry, let's say, in clay landslide. What is its effects, its role? Because very often it actually is an overlooked component of the soil behavior. I really love clays because among old soils, they are the most complex, I would say. So clays are hydrated phyllosilicate minerals. They have a complex structure inside. They are basically made of a succession of sheets of tetrahedral silica and octahedral alumina, and depending on the way this layer, this very thin layer, we are at Armstrong's size, thickness, depending on the way these layers are stacked, you can obtain different clay minerals. And these different clay minerals actually have completely different properties. You can go from quite compact stacks, which do not even have much activity. They are very stiff, very hard, like those of chlorite, to different structures that can, let's say, exhibit a plastic behavior, interact with water in various ways. You go from normally as interesting clays, which are also the most common. We study the group of kaolinites, that of illites, which you see in the figure, and these smectites in some combination. Smectites are very thin layers made of 3 stacks with water and ions in between, and they have actually an enormous surface area, if you think. So these are very thin sheet, like like proof pastry, basically, very thin layers with something in between these layers. If you consider that a single gram of monorelonite, which is the most active clay type, has a surface area, an outer surface, which is exposed to the elements, to water, to air, of about 800 grams per 800 square meters per a single gram of monorelonite. Now, interestingly, the surface of this clay is not even electrically neutral, because thanks to isomorphous substitution in the silica layer, typically sometimes silicon is replaced with aluminum. In the octahedral layer, aluminum is typically replaced in some sites with magnesium, with iron, with manganese. You have a net negative electrical charge on this surface. This charge generates an electric field. The amount of charge is actually pretty large. In a monorelonite, it can be up to 100 milliequivalent per 100 grams, so 1 equivalent per kilo in monorelonite. It's pretty large value, which means that the electrical field on the surface is pretty strong. What does this electrical field do? Well, first of all, clays exist in a hydrated form, so they are surrounded by water molecules. Water molecules are, on average, neutral, but they have a separation of charge because of their inner arrangement between hydrogen and oxygen. So there is a partial positive and a partial negative charge, a dipole, and this dipole actually orients itself inside this electric field, and basically the positive part, the hydrogen, is more attracted to the surface of the clay, while the oxygen is repelled away. All these attractions form a certain structure of absorbed water, we call it absorbed water, surrounding this clay. So the so-called diffuse double layer. In these layers, water is more or less tightly bonded to the surface. You have a stern layer where the first molecules of water are really bonded. It's called crystalline water there. It's almost like frozen water in the sense that it behaves like a solid. You cannot remove it. And while you go farther away from the surface, water is more free because it feels the electrical field less. Water, it's never only water, H2O. You always have an electrolyte. Mainly, you have ions dissolved in any water, groundwater, seawater, and the ions also are either attracted, the cations, or repelled from the surface of the clay. Those are the anions. So there is all a sort of interaction around the surface, and this interaction actually causes a variation in properties of this clay. Just to show you, I see that the slide comes with a little bit of delay, but eventually it will get there. The first 4 molecules of water basically are that those of the stern layer are responsible for a crystalline swelling in clay. So if you start with a dry clay and you provide water, for example, through air moisture, imagine you have clay straight from the oven and you put it in a container where the air is humid. Water will be attracted to the surface of clays. It's a hydrophile, the clay, and it will start to occupy this tightly bonded, to form this tightly bonded layer around the clay particles. One layer, then a second layer, then a third, then a fourth in discrete fashion, up to 4 layers. Then the charges are balanced enough to produce a diffuse layer, and that's what happens when you continue to saturate the clay in this way, because 4 layers of absorbed water is still not saturated clay. The clay is completely unsaturated. Then you have a formation of diffuse double layer up to full saturation, where you basically start to have free water in the pores. This free water in the pores is what is responsible for the permeability of the clay, which is typically very low, and that's because most of the water, especially in certain types of clay, is actually absorbed. It fills the surface of the clay. It's close enough to the surface of the clays to be electrically attracted. Only part of the water is free to move in the pores. I find these are publications from Professor Di Maio from my institution in Italy, about 20 years old. On the left, you see sedimentation tests. So what she did is basically she put a spoon of clay, a spoon of dry clay, in a cylinder with about 1 liter of water, and let it mixed it to produce a suspension, and then let it settle down over time. And she noticed that depending on whether she had pure water, distilled water, or a concentrated sodium chloride solution, which could represent a condition like seawater. These are marine clays that are formed also in marine environments. So if you take a sodium bentonite in distilled water, which could be representative of condition at the bottom of a very pure high elevation lake, it settles with a high volume. That's because the diffuse double layer are very nicely developed, because there are no ions counterbalancing the charges of water. So the effect of the surface charge of the clay is felt for a long distance, and this double layer can fully develop. If you have a salt solution, there are cations. There is the sodium in the solution, counterbalancing the surface charge, which is negative, of the clays, and so the diffuse double layer are much shorter. The volume is smaller, and not only the volume is smaller because the structure has a lower porosity, because the particles are basically shrunk, because of the smaller diffuse double layer. Not only, actually, the porosity that is left there is free for water to move. And in fact, a bentonite in a salt solution even though it's more compact, has a lower volume, actually has a much higher permeability, 2-3 orders of magnitude higher. The opposite happens in another type of clay, which is the kaolin. Kaolin is a kaolinite-rich clay, where in water the structure is more compact, in salt solution the structure instead is more open with a larger volume. Not only the volumes change, but also the timing of this sedimentation process. If you want to make a suspension of clay settle in the clean water, in distilled water, it's going to take years. This is how long it took to get the first picture in distilled water, 1,000, 2,000 days. So basically several years before you got a clear supernatant above this suspension, because bentonite, non-morillonite particles are really, really tiny and really they don't settle. If you have muddy water with bentonite and you don't have ions, this muddy water will stay muddy for a very long time. It will never clear up. But if you have a salt solution, so the same clay in seawater, or if you add salt to the water, it's going to flocculate and settle within minutes, if maybe 1 hour or 2 maximum. So the sedimentation, because the particles flocculate, in fact, they get bulky, and so they precipitate. Basically, you have a precipitation of the clay. Very, very interesting. But if you move farther from the sedimentation, so it's where the clay is actually formed, to the basic properties, you will also see, now that the slide comes up, that if you do a basic identification test of a clay, liquid limit, let's see just the right part here and not complicate our life with non-polar solution. But if you have a clay and you prepare it for a liquid limit test, which is a standard test in the laboratory, you do it with distilled water, you will obtain very large value of liquid limit. If you prepare the same material with a concentrated salt solution, you will obtain much, much less liquid limit, and hence you will obtain less plasticity index, less activity even the clay. Basically, the salt solution is inactivating the clay. It's making it stronger by inactivating it. So you see the big difference when you go from 0 to even small concentration and then larger concentration. If you then are in a technical laboratory and are testing these clays in water or in salt solution, you can also see what happens in an odometer test. Those are really beautiful, especially in morillonites, and you see the left part of the slide, because morillonites, not only after suspension, they are compressed, or after preparation with standard metals, they are compressed, they stay with very large void ratio, very large porosities, and even when you load them and then unload them, they recover that porosity, because the double layer, I say, in general has an elastic response. So you can compress it and then it swells back almost to the initial value after structural rearrangement, but good part of the behavior is recoverable. This does not happen in a salt solution. And think that a pure bentonite might have, at low normal stress, those are typical of landslide, void ratio of 5, 7, 10, but the same clay in a salt solution has void ratios only of 1, which are basically comparable to those of the kaolin. So you basically, by changing the pore solution, you are changing completely the volumetric aspect and the volumetric behavior of these clays. Not only you can prepare laboratory samples with a salt solution, you can actually expose samples to a salt solution during the experiments. You could make a test in which you start with distilled water and then you expose the sample to a salt solution during the experiment. Or you can do the vice versa, which is more interesting because it's closer to a natural phenomenon. You imagine a clay that is sedimented at the bottom of the sea, and then it's covered with more sediment, so it's loaded. Then, because of tectonics and erosion, is unloaded, and this layer of clay now is part of the slopes of a mountain. It's actually what happens in the Mediterranean. The Apennines in Italy, those are made of marine clays that are now exposed to rainwater. And what happens when you expose this clay to rainwater or distilled water in the laboratory, this clay swells enormously, enormously, and become also much softer, much more compressible. This swelling is associated with a weakening, a softening of the material. So you can already think that clays, marine clays exposed to rainwater or to fresh water from aquifers are certainly more prone to slope instability phenomena. They can flow down in earth flows, basically. They can slide because of the weakening. And we see this weakening, of course, not only by the volumetric response, especially we see it in shear tests. Very briefly, you can conduct triaxial tests on samples that are saturated with water or with the salt solution. You will see that for active clays, typically the material in water has half the strength of that in salt solution, saying that when the clay is born at the bottom of the sea is strong. The clay on the slopes that we find now on the slopes and in the landslide is much, much weaker. This can be indeed a problem. You see this in triaxial tests, you see it even better in direct shear tests, in ring shear tests, where you are actually looking for the long-term, large deformation behavior of this clay, which is the typical condition in the shear zone of landslide. Again, an active clay like this one on the left, in a concentrated salt solution in seawater will have a residual friction angle of 15, 20 degrees and even more. The same clay prepared with or exposed to distilled water, or think of rainwater, has a friction angle that is not 20, not 15, not 10, it's only 5 or 4 or even 3 degrees. And that means that a slope made of this clay can have landslides almost on flat land. They can go when the slope is just 5 degrees, 3 degrees only. This is just saturated material. There is no effect of pore water pressure. I mean, even in drain condition, just because of the loss of salt, this material is so weak that can slide in and form indeed very gentle landforms. Now, what are the actual implications of all these for real landslides? I will try to be very quick because we have been studying with the University of Basilicata in Italy a system, I would say, of landslides in a section of the Southern Apennines in my region, which is Basilicata, where you do find indeed many slow-moving landslides. Roberto, can you hear me? Yes, because I think it disappeared for a moment. Okay. You have many slow-moving landslides in slopes that are really gentle, less than 10 degrees. These materials are active clays, and if you see their behavior. Now, I don't have the time to go into the specifics of this landslide. There are normally millions of cubic meters. They are earth flows that move very slowly. They are deep, 20, 30, 40 meters deep in some cases. They move millimeters per year, centimeters per year. They are creeping landslides, so-called. They do respond in a certain way to the external environment, to the rainfall. But what is interesting for me to show is how these clay layers present themselves in terms of pore water composition. We did a number of experiments in which we evaluated the composition of the pore fluid of landslide soils, of the stable formation, of surrounding areas also. And what we found is a profile of the type which is shown here. In the years, actually, we did many of these profiles, not only for this landslide, for other landslides, and also for other landslides in other regions in the Apennines. And all of these experiments confirm one thing. There is a profile showing a transient response, a transient behavior. Something is happening in this formation. These clays are also today losing their salt because they are exposed to rainwater, they are exposed to freshwater aquifers. What is very interesting about this vertical profile of concentration is that you find basically zero concentration at the surface, but then rather quickly you reach very high salt concentration. Now, in these specific locations in the landslide, at depths of 20 to 30 meters, you actually find a composition of pore fluid which is very close to that found in the seawater, basically. And that means that after millions of years, these clay formations, which have emerged millions of years ago, but they are now at the surface because this mountain range is eroding. So basically you have formations that are coming up to the surface, and with all this time, they still preserve the original pore fluid, which is going away now that the pore ions are going away as we speak, let's say, and they form these beautiful profiles. Now, I've already shown you results of shear tests, but I would refer them again to those, specifically to those, to the case of this landslide. And in this material, which is not a monomer sunny light, has friction angles in distilled water, which we evaluate in the laboratory of 8 to 9 degrees. But if you use undisturbed samples, or you use the original, the natural pore fluid, you will get 12 to 14 degrees of friction, which actually correspond to the results of back analysis. So if you actually want to do a back analysis in marine clays, you have to use not standard laboratory tests, but laboratory experiments done with preserving not only the clay minerals, but also the pore fluid composition. Interestingly, if you expose this material to more concentrated solution, you will get higher strength, and even much higher if you change sodium with potassium, just because some more things happen within the clay. But basically also here, from behavior in natural condition, 13 degrees of friction, probably original seawater, 15 degrees of friction, distilled water and current surface behavior, 89 degrees. There is possibility, if you want, to replace the pore fluid with something else, potassium instead of sodium, and actually obtain incredible strengthening up to 20 degrees of friction angle, which is actually a suggestion, a way to possibly stabilize this landslide. I would like now to show you briefly also a couple of tests that we also did, where instead of conducting conventional direct or link shear tests, we modified the apparatus to conduct shear creep tests, meaning that we applied conditions more like to those of a real landslide. We applied a constant shear force. Landslides are not moved by a motor that pushes them, no? They are moved by the gravity, which is more or less a constant force, of course, with caveats, but basically a shear creep test is closer to natural conditions. And if you prepare a sample with a concentrated solution, I show you now in the entire snapshot, with a concentrated solution, so that there is no creep displacement because the material is strong and the shear force is small enough, but then you replace the solution with distilled water, causing a weakening, which is the same weakening that it might happen because of exposure to rainwater. You are weakening the material, reducing the safety factor of the system. You are triggering deformation, you are triggering a secondary and a tertiary creep until failure. So you can activate a landslide by making the soil lose ions, lose the seawater being replaced with fresh water. I will skip on some detailed explanation on what happens in this experiment, and also, of course, I am welcoming questions in live or even also later. No problem, you can contact me to tell you something, and because I want to reconnect to the presentation by my colleague Marco Locke, who happened before mine, not later, but still I would like to reconnect to that, and moving from the topic of chemistry to that of temperature. The thing is that chemistry chemical reaction, in this case ion diffusion, not chemical reaction, ion diffusion. So the loss of ions in the slopes is actually a very, very slow process. That's because the permeability of these clays is very low, and diffusion coefficient of ion in the slope is also very low, and because the slopes are big anyway. You know, in a laboratory specimen, this diffusion happens within days or weeks. You can imagine, and the specimen is a few centimeters. In the field where you have a slope which is 1 kilometer long and there are formations, and formation is 100 meters deep, well, the things happen on a completely different time scale. So this is a simple exercise of modeling where on the left you see a profile of concentration. If you started with the entire slope at seawater concentration, 35 grams liter of ions, and let it be exposed to rainfall, to rainwater from the surface, which triggers some seepage inside the slope. After 1,000 years, you see that you are starting to remove the ions, but basically you find very high concentrations already at 15, 20 meters. So at the depth of 20 meters, you are already pretty close to seawater concentration. At 40 meters, you really have a seawater concentration. Now you see the concavity of this profile, and see on the right the profiles that we actually measured in the field. This is not at all a steady state condition. It's a transient, it's an initial transient, meaning that this surface layer has not been exposed to rainwater for long enough. I believe that because with erosion, this is kind of a fresh layer of soil that has been exposed and is being softened and weakened by the action of rainfall. Of course, this is an example, very simple, with homogeneous slope. You could imagine that instead you have discontinuities, you have a softer landslide material over a harder, more consistent formation. You might have a shear zone that might be more permeable also than the formation, which is over consolidated. We prove with modeling that the presence of a landslide actually accelerates the loss of ions, because that softened moving material is losing ions faster, but overall, still this transient is very far from a steady state condition. A steady state condition with a salt source, which is very deep, it's hundreds of meters deep, would mean almost complete depletion of the ions in the first 50 and more meters of the ground. And this steady state condition can be reached in many tens of thousands of years. So the take-home message from this is that the ion composition, the ion concentration in the pore fluid affects the properties of clays, of clay formation incredibly, but the change of properties with time, which is due to the variation in ion concentrations in the pore water, is very slow. It's a very slow process. It's not a process that can explain the activity of a landslide from one year to another, unless something big happened. It certainly cannot explain seasonality for as long as the material remains saturated, because if the material desaturates, it's another word. But in the shear zones that are deep, there is no way changes in pore fluid composition are so seasonal or so quick to explain a sudden reactivation of a lens. They can, however, explain very slow, persistent creep displacement, which is what we observe. We observe this because as the material is sliding down over gentle and more gentle slopes towards the river valley, it's actually still losing more ions, still getting weaker, and still continuing to move. Millimeters per year over scales of thousands of years actually can make sense. And the landslide that we are studying are actually landslides that exist for hundreds of years. In fact, this kind of slow moving, slow erosion of the slopes. But now to reconnect to the topic, I want really to make a little change of topic in the last minute, to the topic of my colleague Marco Locke. There are other things that can explain seasonality in landslides in gentle clay slopes. And one of these things is, of course, rainfall, the patterns of pore water pressure, but that's not enough, because even temperature can be responsible for a seasonality in behaviors. My colleague Locke and I did an experiment in data-driven modeling where we took the clay slopes in the Apennines, the gentle clay slopes in the Apennines, and we made a susceptibility mapping using a small number of covariates, including temperature, to see whether actually temperature could explain the activity of these clay slopes. And we were very, very surprised when we found that in our susceptibility maps, the land surface temperature of these slopes was actually a good predictor of instability. So we found that warmer slopes were weaker, and we demonstrated this in the laboratory, like Marcus showed you, were weaker and so consistent with more activity, more landslides in certain areas of Italy, of my region. This is Basilicata. One of these landslides is actually the landslide that I showed you before. Also, this is consistent now with a pattern of warmer slopes, weaker, meaning weaker slopes. Now, if you think about this together, now the two topics, chemistry and temperature, seem completely disconnected. But in reality, the fact that higher temperatures correspond to lower strength in other series as well, higher compressibility, also, is actually very consistent with chemical processes, chemical reaction, and chemical processes that happen within the clay in the microstructure. Think of thermal expansion, so it's physics. Think of thermodynamic reaction. Think of the shift of a chemical equilibrium reaction between two parameters, but two states according to temperature. When temperature increases, water swells, minerals swell, water gets more fluid, the bonds are stretched, the double layers expand, the material softens, and so the strength also can decrease. I would like to probably, without even showing the last slide, I would like to conclude this presentation with this, Roberto, and I wonder whether there are any questions from the audience. And thank you very much for your attention, of course.